to MSE 1593 Fundamentals of Material Science, the graduate class. This is going to be team taught by me, Ranji, and Dr. Pankaj Sarin. The following is the um, contact information for me as well as for Dr. Pankaj. You can contact us if you have any questions. This is going to be the video lecture for this class. We might be covering more information, so I have posted the syllabus, so please go take a look at that. So basically, our course objectives are to um, explain the relationships between different types of atomic bonding and the atomic structure, because the atomic structure is going to define the material properties and their behavior. Then we are going to talk about the effect of defects and their role in the deformation and failure of crystalline solids. I also teach a class on manufacturing where we talk about the manufacturing of different components and material from different materials, where the defects are going to be the main reason why it's possible to make components. So there is a give and take between defects and the properties of different materials. Mostly we will be talking about crystalline materials, although very briefly we will also talk about amorphous type of materials, but we will try to limit ourselves to crystalline type of materials where there is order over longer distances in the crystalline structure. Then we will talk about the thermodynamic principles and their effect on phase diagrams to explain the evolution of microstructure and how that changes the properties of your materials and therefore the components. Then we will talk about diffusional and non-diffusional phase transformation, especially from an elevated temperature point of view. Then we will conclude by talking about microstructure property processing relationships for various material types, because that is the basic principle behind that is used for the manufacturing of different materials and components. This is a textbook. It's called The Principles of Engineering Materials. It's a very good read. If you go on Amazon, you should be able to find a copy of this textbook for about between $30 and $40. But if you buy buy a new book, that is going to cost you about $100. But we would recommend that you should only go to the cheaper version if you can. And the first class we will talk about a very brief introduction, bonding, crystal structures, notations, and point defects, etc., which will be the basis for our future classes. So, especially in crystalline materials, what are the different types of bonds that you will find? So let us define what are bonds, especially primary bonds between atoms. Those are the forces that tend to hold the atoms together. And the secondary type of structures, polymers, are not really covered here. In the first case, in the primary bonds, they are controlled by the electron structure of the atoms. So you may recall that the electron states are designated as follows, like, if it is carbon, then it is 1s2, 2s2, 2p2, etc. So that covers all the atoms and the electrons, mainly the electrons. And The inner electron state is a principal quantum state, and the outer electron state is a state in which the electrons move, which will control the bonding between different atoms. So looking at carbon itself, so you have a nucleus that is surrounded uh, by the s orbit that has got 2 electrons, which is spherically symmetric, and the the second orbit, the p type, that has got 4 electrons. So they are not really symmetric. The s electrons are symmetric. So I don't know if you have seen this kind of an electron configuration chart. So the s orbit can hold up to 2 electrons, and the p orbit can hold up to 6 electrons, and the d orbit will hold up to 10 electrons. So how does nature fill these orbits? It's this principle is called the Pauli's exclusion principle. So it is dependent on the number of electrons, which in turn is related to the atomic weight of your atom. So you have in the second orbit you have 2 s electrons and 2 p electrons. So higher the number, further removed are the electrons, and each s orbit can hold a maximum of 2 electrons, and the p orbit can hold 6 electrons. So if you have a higher atomic weight number, then they would have more electrons in the p orbit till they are complete and things like that. So what does each atom try to do? Each atom will try to combine those electrons in such a way that the orbits can hold the maximum number of electrons that it can hold, because that is the energetically stable situation, which is the noble material configuration. So how are bonds formed between atoms? The bonds between atoms are dependent on the electron configuration of the atoms. And the driving force for any of those systems could be a collection of atoms, a group of atoms sitting in vapor, etc. And this works on the principle of energy minimization, which will be the least possible value, which is the noble material configuration, noble gas configuration, like argon, helium, etc. That will give you the least amount of free energy, which is what the materials will try to do. The thermodynamic free energy is expressed in terms of the interatomic electronic potentials. So there are a couple of different rules for bonding, which is that first and foremost, there is a tendency for atoms to do the following. They like to fill the outermost s and p orbits, sometimes called the valence electrons, so that they can adopt the inert gas structure, which I said before, which is the energetically lowest energy structure. So based on that, there are 3 basic types of bonds that are formed, especially in crystalline materials. The first one is called an ionic bond. You have to have 2 unlike atom types, and those bonds are not directional, and there are no more free electrons after that. Then the second one is a covalent type, and you can either have the same type of atom or an dissimilar type of atoms. And in this case, those bonds are directional in nature, which actually contribute to the strength of that material. For example, if it is a ceramic, you have both, in ceramics, you have both ionic and covalent bonds. And the covalent bonds are directional, and therefore ceramics are typically stronger than metals. Here again, you do not have any kind of free electrons. The third type is metallic, and you can have like or unlike type of bonds, and they are not directional either, but there are free electrons. And we will come to the description of those different types of bonds as we go along in these uh, slides. So the first type is ionic bonds, and they can, as I said to you, they can form between two different or unlike type of atoms and not between the same type of atoms. So, for example, if you have sodium and fluorine, it is not between two sodium or two fluorine, but it is between sodium and fluorine. So ionic bonds are between two dissimilar type of atoms. There are two key processes in bonding. The first one is electron transfer, which comes to ionic, and the second one is electron sharing, which happens in the case of covalent and metallic bonds. So for example, in the case of ionic bond, you have, for example, it is sodium and chlorine. You have 7 electrons in the outermost shell in chlorine and 1 excess electron in sodium. So they both attract each other, and so sodium donates 1 of its electrons to make it whole to 8 electrons, and chlorine donates 7 to sodium, so that forms 8 for sodium also. So sodium gets 8 and chlorine gets 8, and the attraction between those electrons is mainly due to electrostatic charges. So as you bring them together, they will attract and form a type of bond. So the second kind is covalent bonding. So in the case of carbon, you have 2s2, 2p2 in the outermost shell. So two carbon atoms can join together to go to 8. So they would form 8 electrons. So they would share electrons. So, but there are also different types of covalent bonds that you can see in the case of carbon. Like for example, there could only be one carbon could be joining with 4 other carbon atoms and so on. So the whole idea is to get to a total of 8 electrons in the outermost shell. So because the p bonds are directional in nature, they are localized in 3 directions. So in this case, it is called sp3 hybrids. So they can, when they form, they will form a directional type of bond. So the classic examples of covalent bonding, the most common one is diamond and silicon. Then you also have germanium and gallium arsenide. Those electrons are tightly bound and they cannot get out. So there are no free electrons in covalent bonding. The third kind of bonds are called metallic bonds. So for example, if you have a metal type of material, so metal, you have 1 excess electron, and sodium would like to go to 8. So all those atoms, at least 8 of those atoms will share the electrons on a time average sense, and those electrons will form some kind of a swirl. I mean, like, it is floating around on the surface and it is not localized and so free to move. So that actually contributes to the conductivity of metals. So there is all those electrons will start floating, and on a time average sense, they will form a total of 8 electrons over a total of 8 atoms and so on. Or if there are 2 electrons, then there would be 4 of them getting together and so on. So each sodium atom will have 8 atoms around it, so that they will have 8 electrons in its outermost shell. It may not happen in non-metals because of energy considerations. In this class, we are going to be talking mostly about crystalline solids. There are other kinds, liquids and gases, but they will not be covered here. And crystals have a property called long-range order, whereas amorphous solids have atoms in non-specific locations. So you have polymers and glasses and things like that, they are all amorphous, whereas in the case of metals or ceramics and things like that, they are crystalline in nature. So all these bonds have to have atoms in specific locations. They have to have order. So which means that they have to have some kind of a structure or mathematical array of points. So you have points in space, and then each of those points are going to be associated with an atomic group, and it is called a basic structure, a basic for the structure. So you should see in the textbook figure number 214. So please take a look at that if you want to see what those are going to be looking like. And so there are 2 types of atoms, and they will have a particular arrangement of particular atoms. So this is the lattice structure, and each of those lattice points have a basis group. So the point lattice plus the atomic group is the periodic atomic array. So that gives you the crystal structure of any material. So each of those lattices can be defined by 3 lattice vectors A, B, and C. I mean, you can rotate them, but they are basically, for argument's sake, you say that they have 3 lattice structures A, B, and C. They are vectors for all intents and purposes. And many of the structures that we will be looking at least A and B are going to be equal, and C might or might not be equal to A and B. So how do you define point lattices? They are done in 2 steps. First, you have to define the crystal system, and then you have to define the Bravais lattice or unit cell. And they are all given by the correlation between the A, B, and C vectors. So you can construct simple volume elements using the unit vectors, and those unit cells can be used to fill all the available space. Then you will go and put one basis group on each of those lattice points. Again, we will go more narrow, so we will try to focus mostly on the cubic system because that's the easiest to understand. So the cubic system is A equal to B equal to C, and the lattice parameter or the sides of that cube is called A, and the points in that cube could be either corners or in the center of that cube or in the center of the faces, and that is used to construct the point lattice. And the points must be chosen such that the following will happen. So here again I was telling you, so there are a total of 14 distinct ways in which you can attain or achieve a point lattice. So this is figure 216 in the textbook. So you have multiple types of lattices. So the cubic ones are the bottommost 3 ones. So what is a point lattice? It is a lattice such that each point has identical surroundings. So as I mentioned to you, you have a lattice which is defined by the Bravais lattice as 14 different systems, and then you have one basis group, atomic group on each of those points. So there are 14 distinct ones based on 7 different unit cells. So in the cubic systems, which is the simplest system that you can think of, there are 3 different point lattices. They are called simple cubic, body-centered cubic, and face-centered cubic. So I hope you remember all that. So they all have specific types of geometrical relationships. So where n is equal to the number of lattice points per unit cell, simple cubic, it is equal to 1. Why? Because there are 1, 2, 3, 4, 5, 6, 7, 8. They are shared between 8 other unit cells. So for one unit cell, you essentially have 1 lattice point. In the case of body-centered cubic, you have 1 single atom in the center and 8 atoms that are shared by 8 other groups. So that is a total of 2. And in the case of face-centered cubic, you have 1, 2, 3, 4, 5, 6. 6 faces of the cube that are shared by 3 other so each is shared by, so 6 atoms shared by 2 each. So 2 cells. So which means there are 3 specific atoms, and then you have these 8 atoms that are shared by 8 other groups. That is a total of 1. So 3 plus 1 is equal to 4 in the case of face-centered cubic. So you can have symmetry of operation. So you can rotate this cubic lattice by different angles. So if you rotate it by a certain angle or move it by a certain distance, then they should remain the same. And why this becomes important is where you are going to be talking about different kinds of atom movements. So that's where these things will come into play in order for you to understand this better. So one important class of operation is rotation, and if you rotate it by its axis 90 degrees, it should give you the same cube, but just that the atoms are going to be in rotated locations, that's all. So if you rotate that, then this will go like this. This lattice will remain the same essentially. If you did not look at it before rotation, after rotation it will look really the same, except that the atom positions of the previous lattice cube have just changed, that's all. So you have 4-fold axis of rotation for the edge. In a sense, it is symmetrical, so you can rotate it 4 times to get to the same old position it was in before you started the rotation process. And where this also comes into play is where you have different types of properties for the material. For example, if you have current moving through a crystal or moving through a material or a wire, the wire is made out of materials that have atoms in them, and so if you rotate them by 90 degrees, it does not change the current, but rotating by an odd angle, it may change the current because the crystal will recognize that. Because, for example, if it is not a symmetric lattice, If you rotate it by a non-symmetric type of degree, then the property of the material will change. So in this case, you only have, I mean, for a cubic lattice, you only have a finite number of angles through which the crystals can be rotated. So those rotation angles are 0, 60, 90, 120, 180. And because you all have, I mean, it has to come back to 360. So if you don't have that, it'll be difficult. I mean, you may say that you can do 36, but the angle will not be the same. The atom positions will not be the same. Once you do it by 36, the angle positions will not be the same. But in the case of 60, 90, 120, 180, the angle, I mean, the atom positions are going to be the same afterwards. So let's take the example of copper. It's a very simple structure, and it is very similar to aluminum, nickel, etc. And the lattice is FCC, and the basis is 1 copper atom per lattice point. You have cesium chloride. This is not really BCC structure, and although you may say that there is one center atom, but it is not body-centered cubic. So as I said to you, there is one lattice point in simple cubic. So each lattice point has to have one basis group. What is a basis group? Basis group is one atom of cesium and one atom of chlorine. So there are 8 atoms of chlorine on the end points. So ultimately it is contributing one chlorine atom to this unit cell. And then you have one cesium atom in the center. So that is contributing one cesium atom and 1 plus 1 chlorine atom. So there is one lattice point. So this is contributing one cesium chloride basis group to this lattice. Sodium chloride, you have the basis is 1 sodium plus 1 chlorine. If it is FCC, there are 4. There should be 4 atomic groups. So which means that 4 basis groups should be there in each unit cell. So this is a little complicated to understand. So there are actually atoms in the other points also. So the outside points are, so those are 2 interpenetrating FCC cells. So the sodium and the chlorine are in the cell positions of each of those unit cells. So ultimately they will have a total of 4 basis groups for this one single unit cell. So let us come to an understanding of directions and planes. Why do we want to understand directions and planes? How do we make materials? You have to deform the materials. So which means that you have to move atoms and planes of atoms. So which means that you need to know which direction you have to move in, which planes you have to move in, etc. So you have to understand the basic principles of directions and planes. So how do you define a plane, a direction? You have to give the coordinates of that point in space, and you have to draw the vector from to the point from the origin. This gives you the direction. So square brackets gives you the direction, and the integers, they have to have integers that are the coordinates of a point. If you have a direction from the origin to a negative direction, then you will have u bar, which will be u bar, v bar, w bar, which will be a negative direction. It depends upon where the atoms are located. Okay, so for example, if you take the reference axis as 1, 2, 3, you should be able to calculate the direction of that plane. So here are some examples of that. So for example, here, uh, this one, this direction is 1, 1, 1, this direction is 1, 0, 0, this direction is 0, 1 bar 0, because there is no atom point in the, the atom is located in this point, so this one is 0, 1 bar 0. This one is 1, 1, 0, etc. So here again, the vector need not even go through the origin. So suppose you want to draw arbitrary from this point to this point. You need to know the starting point and you need to know the end point. So if you take the difference of that and make it integer units, then it should give you the direction. So that's about it for class 1. Please go and look at chapter 2, and you should have more details there. I'm not going, I would like to cover as much as possible, but please go take a look at the textbook, okay?